We are moving into 6.2. 6.1 was using integrals to find the area between curves. So not just the area under one curve, but the area between curves. 6.2 we spend 3 lessons on, and this is all about using integrals to find volumes of solids. So the first 2 days, today and tomorrow, are volumes of solids of revolution. So there is a region that's being rotated around an axis and it's creating a solid of revolution. There's 2 methods to use based on the region you have, what you're rotating around. Today we're looking at the disk method. Tomorrow will be a washer method. And then the third day is if you have just the volume of a solid, but it's not being revolved around something else. You're just given the solid as it is. I need it quiet. I do not want to be talking over you. If you're not paying attention to volumes, it's going to be very confusing. So you need to know how to find these volumes. I first have a general case, just kind of so you can understand, kind of like we built into what an integral is as a limit of Riemann sums. This is kind of the same thing, showing you why an integral can be used to find the volume of a solid, of revolution in this case. So we're going to start out with just a general case. Say you have a region bounded by some function f of x on an interval from a to b for your x values, and then it's also bounded by y equals 0 in this case, so it's bounded by the x-axis as well. So I'm just going to draw a general curve. It's going to kind of look like a square root curve, but it doesn't have to be a square root curve, just a general curve, y equals f of x. From a to b, so I'll say a is here, b is here, and then it's also bounded by y equals 0, which is the x-axis. So I'll actually draw vertical lines here. So this is our region. And this first part is just going to be a little bit of review. So where we started when we were first talking about finding the area under a curve is we said that we could divide the interval from a to b into equal subintervals. So we would find delta x based on what our n was or how many rectangles we wanted. So you divide a to b into equal subintervals. So I'm just going to draw one general rectangle here. Say this is our rectangle. And we would find the area of that rectangle. So we know that the width of that rectangle would be whatever our delta x is. And then the height of the rectangle, we would have to choose some x value on that interval to substitute into the function to get the height. So we could have used the right end point, the left end point, the midpoint. They called that the sample point. They listed as x sub I star. That just means any x value that's in that subinterval would be substituted into the function to find the height. So the area of just one rectangle was the height of f of x sub I star multiplied by the width, which was delta x. So that was one rectangle. And then we wanted the sum of all of the rectangles from a to b. So I'm just going to include before this our sigma notation. So the sum from when I is 1 to whatever our n value is. So that was what we were using when we were just using right endpoints or left endpoints or midpoints. And then we said, really, to get the exact area, you have to let the number of rectangles become more and more and more or approach infinity. So we took the limit of this Riemann sum as n approached infinity, and that was the exact area that was under the curve from a to b. And then we said this limit, that's what was defined to be an integral. So therefore, this was equal to the integral from a to b of f of x dx. Okay, so just a That's just a refresher of what we covered at the very beginning of chapter 5, how we started with rectangles and then defined that to be an integral representing area under a curve. So now the question is what it says below that. What if we take this region that I've colored up here and we rotate it around the x-axis? So I'm going to redraw this below here, or do my best to do this. This is where it might be tough for some of you to visualize what you're creating, these volumes or these solids that you're creating. That might be tough to visualize. That's okay. Ask questions if you have questions. So I'm just going to redraw my general curve f of x. What I'm going to draw first, I'm not going to worry about the a to b part. I'm going to draw that in a minute. I just want you to picture what's happening here. So take this curve and say it's rotated about the x-axis. So you're going all the way around the x-axis. If you can picture that, it's creating this solid where then the surface of that solid would be a circle because it's being rotated around 360 degrees or 2 pi radians. So if I were to kind of draw what this out looks like, I would see another curve kind of come down like this. I would have a circle at the very end. This would kind of be the solid that's created, rotating around the x-axis. Okay, so now I'm going to draw in, if I, again, included, I'm just rotating the region from A to B, trying to match this pretty well. So all that would mean is I'm kind of taking a slab out of that entire solid that I just drew. So you kind of have a circle on either end. Now, really, you can work through these problems without having to draw this out. So I know I'm drawing it to help you picture it. If it's tough for you to draw out, it's tough for you to picture, it messes you up, you can work through these problems. You don't have to draw out what it would look like. So if that's not helpful to you, it's not a necessity for you to actually have to do that. I'll show you what you should be able to draw, what you have to identify to be able to solve these problems. So then what I want to kind of build here, or the question becomes, before we were looking for area under a curve, now we're trying to say, okay, now we have this solid of revolution, how do we find the volume of it? So I don't want just the area under a curve, I want the volume of this solid. And how can I use an integral to find that? So I have here finding the volume is similar to finding the area of the region. So again, you'd start out and you'd say, okay, I'm going to go from A to B, divide that into equal subintervals, so get my delta x. So I'm going to just draw in kind of how I drew a rectangle up here. I'm going to start with just one rectangle. Just drawing one rectangle. So again, width of that rectangle is delta x. Again, the height of that rectangle, I would just choose an x value in that interval, call it x sub I star. Sorry, I realized me coloring that in might be hard to see. I'm just writing x sub I star again there. So you would substitute that x value into your function to get the height of the rectangle. That's all the same as before. But just like our curve and our region was rotated around, just think if I took one rectangle and I rotated it around, what would that look like? So if I rotated just this rectangle around, and I'm going to draw this off to the side, this is what's created. So here was my rectangle, and it was rotated around, and it becomes what we call a disk. So this is why it's called the disk method. So one rectangle is like a disk. Okay, so that's what is being said down here. You're starting out with a rectangle, rotate the rectangle around, creates a disk. If I can find the volume of each disk, then I can take the sum of all of the volumes of all of the disks and then take the limit of that sum so that it is an integral. That's kind of where we're headed with this. The question is then, how do I find the volume of a disk? This disc, think if you rotated it this way, it's very, very short. This disc, though, would be a circular cylinder. Okay, because if I just sliced through this solid, the surface of this disc is a circle because it was rotated 360 degrees around that x-axis. So the surface is a circle, and then I have that width, so it would be a circular cylinder. So the volume of that disc, I'm just going to put V sub D, would be the area of that circle, the area of the surface, or they call it a cross section. So as we move forward these next 3 days talking about cross sections, cross section is the shape you would get if you slice through it. If it's a solid of revolution, like today and tomorrow, all cross sections are circles. So it would be the area of this circle multiplied by the width of the cylinder. So the area of a circle, so really I'm going to write this down. It would area of a circle is pi r squared times the width. What would the width of the disc be? The height or the... Nope. What's the width of the rectangle? Delta x, yeah. So the width of that disc is the width of the rectangle. That's still your delta x. So it's pi r squared times delta x. What you have to find then, because this will always be the formula for every volume of every disc, it's always pi r squared delta x. What you need to identify is what your radius is in terms or with respect to your function. The radius is the height of your rectangle. The height of your rectangle is the function evaluated at whatever x value. So the radius in this case would be f of x sub I star. So the volume of this disc would be pi times f of x sub I star squared, delta x. Now, I know this is a general example. It might seem very confusing. As we get to examples, please, if you have questions, let me know. But again, building this to become an integral, I just want to show you the same way I showed you up here with area. So if you start, so now I'm going to kind of build to the volume of the entire solid that's created on the interval from A to B. So just like for area, we started with the area of one rectangle, then we added the areas of all the rectangles, and then we took the limit of that to get the exact area, and that became an integral. So we start with the volume of one disc, and that's this. So the volume of one disc is pi times f of x sub I star squared, delta x. And then you add together the volumes of all of the discs on the interval from A to B. So that would be the sum of that volume from when I is 1 to n. And the most, or the best, or rather the exact volume would be if you let n approach infinity. So now if I take the limit of this as n approaches infinity, this is the exact volume of that solid. But again, a limit of a Riemann sum is an integral. So this means for the volume of a solid of revolution, if when you slice through it you get a disk, which all of them today are just going to be disks, this is the integral you would solve or evaluate. Integral from A to B of pi times your function f of x squared dx. They could be a washer. We'll see that tomorrow.
Like the washer, like with the holes in them?
Yes. Okay, and then the pi here, because pi would be a coefficient, the pi could be written in front as well. What I do want to point out though, so this just explains what we just wrote down, but now you see kind of where that is coming from. What I want you to look at is the definition of volume. They wrote this differently. So notice rather than writing pi times f of x sub I star squared or just pi times f of x squared, instead they wrote it as a of x. And the reason they did that is, like I said, we're going to be talking about cross sections. If you just slice through and you look at the surface, what shape do you have? For a solid of revolution, it will always be a circle. But really, the volume of this disk is the area of your cross section multiplied by your width, which is delta x. So pi times the f of x sub I star squared, or just pi times f of x squared, that is the area of the cross section, which is a circle. That's why they're writing it as a of x. So you would substitute in here whatever the area of your cross section is. So if your cross section were to be a triangle, which it will not be today, then you would have the area of a triangle. Like I slipped that today in there. You would have the area of a triangle there. What's important to realize here is how to get volume. If you integrate area, you get volume. That's what this says. If you integrate area, you get volume. So you're kind of going up a dimension. You're starting with something squared, now you're in something cubed by taking the integral. So if you integrated volume, you'd get something four-dimensional. Yeah. Yes. Okay. So let's actually see a specific example. And for this one, to sketch it, it's going to look very similar to what we just sketched because we have the square root function. So it says find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals square root of x from 0 to 1. So it's always going to tell you the curve that's forming the region. You should have boundaries. You should be told what you're rotating around. It doesn't always have to be the x-axis. Actually, the second example is the y-axis instead of the x. So I would first sketch the region. You don't actually have to sketch the full solid if that's confusing to you, but sketch the region. So if I have, the curve is the square root of x, so like I said, it's going to look like the general one we just had. So y equals square root of x from 0 to 1. So let's just say I put 1 here. This is the region I'm rotating, and I'm rotating it about the x-axis. I'll show you my thought process as I work through these. Now today we're just starting with discs. Like if you were to take a rectangle and rotate it or cut out a slab from your entire solid, it will always be a disc. Tomorrow we'll do washers. So you want to make sure after tomorrow, kind of moving forward, that you know if you have a disc or a washer. Discs are easier. We'll work with discs first. So what you want to picture here, like I said, if you can picture rotating the entire solid, so I would have, if I rotated this around the x-axis, this would kind of be reflected down. This then would be a circle at the end here. But really what you want to picture is if I take a rectangle and I rotate that rectangle, I can see that it's going to create a disc. So what I'm going to do is just kind of draw this disc. On its own. Because if I can come up with the formula for the volume of one disc, I can insert that into an integral. So the volume of this one disk, again, the cross-section, solid of revolution, always going to be a circle. And the width of the disk is the width of your rectangle, it's delta x. So the volume of the disk is pi r squared for the area of the circle times delta x. What you have to figure out is what your radius is. What are you substituting in for r? So, well, this is a general case, not at the x value 1 specifically. It could be at any x value. It's the square root of x. So your height of your rectangle at any point is going to be the square root of x. It's going to be your function. Why? Well, if I substitute in, say, 0.2, I would have the square root of 0.2. If I substitute in 0.5, I have the square root of 0.5. So if I just have any x value, just x, I would just have the square root of x. So your radius, so this is a nice thing to note, your radius is your function. Because if you substitute an x value into your function, you just have your function. But you want the general case, you don't want a specific x value, you don't want just a number. So my radius is my function, so the square root of x. So then I have pi times the square root of x squared times delta x. If you can simplify that, do it. So I know square root of x squared is just x. So I have pi times x times delta x. So that would be the volume of one disk. Now, rather than going through and writing everything out like I just showed you for how to get the integral, I can then go and say the volume then, or the exact volume of that solid would be the integral of pi x. Because my delta x, when I write the integral, is kind of like the dx. So I would have the integral from your x values, your interval is from 0 to 1. So the integral from 0 to 1 of pi x, that is the area of my cross section, the area of that circle, and then dx. What was that? When you find the integral, find the antiderivative, then you substitute in the 1 to get the value. Okay, so now from here, you evaluate the integral. If you want to, because you could always do this, you're always going to have pi in there because pi r squared is the area of every circle. You can write the pi in front because it's just a coefficient. So you really just have pi times the integral from 0 to 1 of x dx. So you're really just integrating x. So what's the antiderivative of x? 1/2 x squared. So I have pi times 1/2 x squared evaluated from 0 to 1. I really just need to substitute in 1. So if I substitute in 0, I have 0. So I have pi times, if I substitute in 1, 1/2 times 1 squared is 1/2. I will just write this so you know I'm substituting 0 as well. So my volume of that solid is 1/2 pi. So the tough part, once you have the integral, it's figuring out what integral you have. That is the tough part. It does look like a ham. Questions on that one? We're going to go through example 2 as well. Okay. For example 2, here it says find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. So again, I'm going to sketch the region that I'm working with. So y equals x cubed. The entire function or entire graph looks like this. We're only dealing with part of it though. Because then we're also bounded by y equals 8. That would be a horizontal line. To say this is 8 here. Yes, Ifer? Yes, so you're just graphing to picture the region. Yep. So y equals x cubed, I have that curve. I have y equals 8. X equals 0 is the y-axis. So the part that's bounded by all three of those would be this part here. So I know I drew this part that's in that third quadrant. I drew that in for y equals x cubed, but I'm not dealing with that part of my curve. And I'm rotating this about the y-axis. So remember, between the 2 days we covered 6.1, when you're finding the area between two curves, you could have vertical rectangles, top minus bottom, or you could integrate with respect to y and do horizontal rectangles, right minus left curve. Your rectangle should always be perpendicular to the axis you're rotating around. So because, for example, 1, we were rotating around the x-axis, we used a vertical rectangle because it's perpendicular to the x-axis, which is horizontal. So here, if the axis we're rotating around is vertical, I should use a horizontal rectangle, but that means my integral will be in terms of y. I'm integrating with respect to y instead of x. Yes, you're going to be doing the right minus the left. So, well, you do. You have the x cubed would be the right, and then your y-axis, x equals 0, would be your left. So, how to work through this or how to picture it if you were to draw this out, it's actually going to look similar to what this one is, just rotated, because this part is what's being rotated around, so it would kind of reflect over. You'd have a circle here. So if you rotated that rectangle, you'll still get a disc. It'll just be horizontal. So I'm just going to draw. I find this helpful just to draw the disc so I can label what my radius is and everything like that. Ultimately, I'm looking to see, can you set up the right integral and find the answer to it? If you don't actually draw this out, you're not going to lose points or anything like that. So still have the volume of the disc. It's the same thing. Volume of every disc is the same. Area of the circle, pi r squared, times your width. But now the width, instead of being delta x, because we need to be in terms of y, it would be delta y. So because everything needs to be with respect to y, that also means because I have the function, y equals x cubed, I need to solve this for x, so it's in terms of y. So if I take the cube root of both sides, this means x equals the cube root of y. So that is really, the cube root of y is the function that I'm using. So your radius would still be the length of your function, but it would be the cube root of y in this case, because it needs to be in terms of y. Or you could think of it, because Quinn had brought this up before, right minus left. Your right curve would be the cube root of y. Your left curve would be the y-axis, which is x equals 0. So you'd have the cube root of y minus 0, which is just the cube root of y. I will substitute that in here. So we would have pi times the cube root of y squared. And you can't really simplify this. You could rewrite it as an exponent, which I would recommend when you're actually doing the integral. What would the exponent be on y here? 2/3. Okay, so the pi times y to the 2/3, that is the area, that really represents the area of that cross section, that circle. That is what you're integrating. So your integral then, the exact following would be the integral from, our limits of integration should be y values. What y values are we in between? 0 and 8. Okay, and then we're integrating pi times y to the 2/3, and then dy. And again, if you wanted to, you could write the pi in front. You could do that right away as well. If you don't write it out in front, it's not going to affect what you're doing. But now, finding this integral, find the antiderivative. Antiderivative of y to the 2/3. 3/5 y to the 5/3. Yep, add 1 to the exponent, which is 5/3. The reciprocal of that new exponent comes down in front. But you could do the cube root of 8 first and then raise it to the 5th power.
Whoa, what is that?
The 8, so this region goes from the y value 0, and it was bounded up here by the y value 8, because we had y equals 8. Well, with that attitude.
Oh.
Gotta believe in yourself, Jake.
No, but that's the price.
All right, so we have pi times, yes, it'd be 3/5 times 8 to the 5/3 would be the cube root of 8 to the 5th power. Cube root of 8 is 2. 2 to the 5th is 32. So they might not, like, this could be a no calculator question where you'd have to calculate that. And then if I substitute in 0, again, I would get 0, so minus 0. So we would have 32 times 3, 96. So it'd be 96 over 5 times pi. This would be the exact value. They probably, well, I've seen questions involving areas and volumes on both the calculator and the no calculator part, but this is the answer. Obviously, you would leave it that way. That's the exact answer. Your calculator would give you a decimal approximation because of the pi that's in there. If you said 19.2, that's fine. But if you're doing this without a calculator, did you did that? Okay. Yeah, 19.2 they would accept. That's still 96/5. Okay, any questions on that one?